Test, test. Test, test. Okay. Testing. Hello?
you to a few of the teams involved this morning. We want to start with the U.S. Space Force. They're responsible for the range operations and
Hi
weather
there.
activities.
Can everyone hear me?
So, Mick, tell me about the range really fast before we get this weather briefing in just a few
Hold
seconds.
on.
Yes, the United States Space Force is responsible for public and personnel safety here at Cape Canaveral Air Force Station and Kennedy Space Center, where we're launching from. So, very important part of the mission today. They are one of 5 teams that are working with us to launch Mars Perseverance on its way this morning. And an important part of that, not only public safety, but is they
Okay. Does it sound like I'm repeating when I'm talking?
Yeah, man. That's fine. That was good.
That's good?
Yeah. I mean, you know, it only just came across, right? That was a big delay.
Yeah, that's okay.
Okay. It's what, a 30-second delay?
Looks like we have 3 watching currently.
Reactor. It's a nuclear battery, and it's actually something that has been developed by the Department of Energy for this kind of a purpose. It's a multi-mission radioisotope thermoelectric generator.
Okay, can everyone hear me? Okay, so without further ado, it is currently 5:30. I'm going to begin the launch coverage. I'm going to have a 20-minute session before the launch actually occurs because this will be an easy way to both explain some of the reasons why this launch is going to be so special and also why this particular rocket is so cool. So as you can see here, we actually have the rocket pulled up in an Illustrator. This is an exploded version of the rocket that will be allowing me to circle different parts while I'm describing them to get a better idea of exactly what I'm talking about. So this particular rocket is actually called originally an Atlas V. And what that means is that it is the 5th rocket in the Atlas line. And the Atlas line of rockets, it actually goes way back. That was the rocket that John Glenn launched off of, which was the first American to orbit the Earth. And before that, that was one of the very first rockets to put American satellites into orbit. However, we've come a long way since the original Atlas I. The Atlas V is currently the heavy lift launch vehicle for the United Launch Alliance, which is an American company that puts different satellites and probes into orbit and into their trajectories that they need. However, you might have noticed on the stream that this particular rocket has the designation of 541. And what that actually has meaning to it. Not only does that mean that this is an Atlas 5-541 as the full name, but what the name kind of means is that it's going to have a 5-meter fairing, which is this part up here. The diameter of that part is going to be 5 meters. It's going to have 4 solid rocket boosters, which are these on the side. You can have either 0 or 1 through 5 solid rocket boosters. And the last number, the 1, means that you have 1 secondary engine. So this is the engine on the second stage, and it comes in 2 variants, a 1 and a 2. So that's what the naming convention of the Atlas V is. Now let's get on to some of the interesting parts about this particular mission. Because this is the second time that we're going to be sending this kind of version of a rover to Mars. Believe it or not, this particular rover, Perseverance, shares 90% of its parts with the last rover that we sent, which was Curiosity. And the reason behind that is that most of the parts for Perseverance are actually the backup parts for Curiosity. However, we're not going to be doing just the same type of science and the same stuff once we get to Mars. Some of the noticeable things that Perseverance will be doing is that it has the first ever in situ resource utilization on board, which is usually shortened to ISRU. And what that means is that we're going to be trying for the first time ever to take the supplies from the Martian atmosphere and turn them into something else. In this case, oxygen. And that's really important not only for when we eventually send people to Mars, but also for when we need to send a return mission, because a lot of return missions, the rockets are going to be fueled by oxygen and some other fuel. So the other experiments on board include an actual sample collection system. And this is really different from the Curiosity sample collection system because it will be caching the samples in little cylinders or tubes and leaving them on the surface. And the whole idea behind this is planning ahead for, we don't currently have any missions in the works for a sample return, but whenever we do, when we get there, the samples will already be kind of nicely packaged for us. So the last kind of large experiment that's going to be really new is actually something called Ingenuity. And I like that particularly because it's a helicopter. Yes, you heard me right. We're going to be trying to fly a helicopter on Mars. Ingenuity is pretty special in that it isn't a helicopter in the traditional sense. It doesn't have like a tail. It won't have a pilot in terms of we didn't send someone to pilot with it. It will be fully automated for its first flights. And it actually has coaxial blades. So what that means is instead of having a single blade spinning around and a tail boom with another propeller that keeps it from spinning out of control, instead it'll have two blades that spin in opposite directions to keep it stable. And this is a really interesting thing because currently it's a proof of concept. We've never flown something on another planet. However, if this works, it'll be kind of the gateway to future more advanced flying missions, including stuff like the Dragonfly mission, which aims to send a quadcopter to Saturn's moon Titan, and a bunch of others. It's very handy to have something that can fly because currently our satellite imagery, although it's really good, can't really resolve more than a meter of detail. So that's kind of like me looking out the window of a plane and being able to resolve a square meter, about 3 square feet, thereabouts. And so Ingenuity will be able to resolve much more than that. Some of the other things that I particularly like as a student from Arizona State University is that we actually built two of the cameras that are going on the Perseverance rover. And so you may have heard on Curiosity they have something called Mastcam. Well, ASU built that, and then they went ahead and built something called Mastcam Z for Perseverance, or the new rover. And that's really cool because it's 2 different cameras, which gives you binocular vision like us humans. It can do depth perception, but it also has a filter wheel. So if they want to look at a particular rock in a particular color for scientific reasons, they can do that automatically with this camera. Because you can imagine it'd be kind of difficult to go up there and change filters every time you wanted to look at different colors. In addition to Mastcam Z, Perseverance will also carry a record number of, I believe, 26 cameras on board, which will help with everything from self-diagnosis of the rover to even things like pinpointing the entry, descent, and landing. Because something interesting about the so-called 7 minutes of terror that make up the landing of a Mars rover is that up until now we haven't really had a well-guided entry, descent, and landing. We've been able to make really good predictions of where it will land, but we haven't been able to really change that when the spacecraft is actually entering the atmosphere. And Perseverance will change that through 2 things. It'll actually deploy its parachutes to slow it down a little bit, or its drogue chutes to slow it down, earlier or later based on where it would like to land. We picked a small landing spot, and it will automatically do the predictions and trajectory calculations to say, hey, it looks like I'm going to overshoot the area, so I'm going to deploy my drogue chute early. In addition to that, the sky crane is going to be a little bit more precise, which will just help us get within about a kilometer of accuracy in terms of landing, which is extraordinarily accurate compared to previous rovers that we've sent. And you might be asking, why is this all kind of important? Why would you want to land close to the landing site? Isn't that why we have a rover in the first place? Because once it lands, it can kind of go drive off to its destination? Well, both the Curiosity and Perseverance rovers have an incredibly slow top speed. And the reason for that is that if anything happens on Mars, it's about a 22-minute delay before we hear it back on Earth. So Perseverance and Curiosity have both been kind of designed to be pretty autonomous. However, as a safety factor, they keep it to around 1 meter per second, which is a very slow walking speed even. Speaking of the speed of the rovers, and particularly their wheels, Perseverance will also carry new wheels from Curiosity. And this is just an example of us taking something that we've learned from Mars, as punishing as it is of an environment, and applying it forward in future exploration vehicles. The Curiosity rover wheels had a very interesting tread pattern, and the way that they were shaped was designed to be kind of springy to help with any kind of impacts that might happen. But the particular way that it was designed actually caused some issues when the rover was driving around. On the Curiosity rover, one of the wheels got punctured, which is not too big of a deal on Mars because they aren't exactly filled with air. They're solid metal tires. And another tire got a couple of rocks stuck in it. And this wasn't too crippling for the rover. It was still able to easily move around. But on Perseverance, we've designed a different type of tread, which will hopefully kind of mitigate the risk of that ever happening again. And that's just a really cool thing to me, because here we are, something that we launched not too long ago in the early 2000s, and it's already been helping us design for future missions, not only bringing back such valuable scientific data. So let's talk about the launch vehicle then, some more. The Atlas V is a very notable launch vehicle. It's launched a lot of things. In particular, this exact configuration of the Atlas V has launched everything from the Curiosity rover to several national reconnaissance satellites. So it's launched classified missions for the Air Force, and it's even launched a lot of the GOES satellites, which are weather satellites up in geostationary orbit that help provide things like the forecast and also help us predict where hurricanes and typhoons will hit. So this particular launch vehicle is responsible for stuff that you use in your everyday life, probably, if you ever turn on the news in the morning to get the weather. Some other notable stuff about this launch vehicle is that you'll notice I keep saying in this particular configuration. And the reason why I say that is that this Atlas V can have several different permutations or configurations. You can change the size of this fairing right here to be 4 meters or 5 meters. You can change it to be longer or shorter depending on the needs. You can change the second stage engine down here to either be 2 engines for more thrust or 1 engine for more efficiency. And you can even change the strap-on solid rocket boosters down here for either more thrust or less thrust depending on what you're needing. Because if you need to lift a very heavy payload like the Perseverance, you might need 4 or 5 or even 5 strap-on solid rocket boosters just to get it off the pad. But if you don't really need that much thrust, you can actually take off several of the boosters and have less thrust, but also less cost and more efficiency. Because this particular rocket, if you wanted to get one, which technically you could, it is a commercial company, but it would cost you about $145 million. Let's just put that into perspective. $145 million for one thing that's only going to be firing for a couple minutes. That's just mind-boggling to me, but it makes sense when you put it into the context of this rocket. I mean, these are some of the most complex machines that have ever left the Earth, and currently they're one of our only routes to space. In fact, I want to direct some attention down to this area of the rocket, the bottom of the rocket, and particularly these two engines at the bottom. These two engines are actually particularly special because these are Soviet-era engines. These exact rocket engines, at least on the current Atlas V, came from Soviet rockets and stockpiles. And that's an interesting thing because you might be asking, first of all, the Soviet Union's gone. Why are we still using their engines? And also, this is a U.S. rocket. Why aren't we using U.S. engines? And it turns out that for the applications of this rocket, these engines just fit the bill really well. And even though the Soviet Union's gone, Russia still has a stockpile of these rocket engines from the Soviet Union. They didn't just throw them in the trash because these are extraordinarily complex pieces of machinery. And it turns out that if it works, why use anything else? So these are, I believe, RS-68 engines. Correct me if I'm wrong on that. But that's just another cool thing about this particular launch vehicle. Some other things. This stage up here, let me circle it. This stage I've been talking about a little bit in terms of how many engines you can put on the second stage. Well, this particular second stage is actually a variation called a Centaur upper stage. And this gets its roots all the way back from the early Atlas I vehicles, and I believe even technically the Thor Able vehicles, which were converted ballistic missiles. But this particular stage is probably the oldest heritage hardware on this rocket. The first stage has been updated over and over from the Atlas II forward, but this Centaur stage, for the most part, has remained pretty close to the same. They use pressurized tankage and an RL-10 or two engines based upon the need. Some other notable things that this particular rocket has carried and will be carrying is actually the Boeing Starliner. So you may have heard in the news something called the Commercial Crew Program, where NASA is using both Boeing and SpaceX to kind of compete against each other in order to get the best ride to space. And as a part of that, Boeing submitted their design called the Boeing CST-100 Starliner. And you might also know that name from the fact that it's made some headlines recently because of a coding error in its one of its test launches, made it kind of come back home early. Everything's fine with the capsule, but that might be another area where you've heard it from. But this particular rocket is actually the rocket that will be carrying that particular spacecraft. And they had to make a couple interesting modifications to the rocket in order to do that, because this rocket doesn't normally launch things with crew in it. And in order to launch something with crew in it, it needs to be crew certified, as NASA puts it. And this particular rocket wasn't NASA certified when they originally started looking at it for sending up crew. And so some of the things that they had to do was they had to adapt it to not use the fairings. So the capsule just sits on the top of the second stage here, directly on top of the second stage, and doesn't utilize a fairing or any kind of mounting hardware. And they're only using 2 solid rocket boosters on that particular variation. So that presents an interesting situation in how do you name a rocket like that? Because normally we're able to follow a pretty standard naming convention. If it has 4 boosters, put a 4 in the middle. If it has a 5-meter fairing, start the name off with a 5. If it has 1 engine on the second stage, end it with a 1. But what do you do when there's no fairing to name? Well, the Boeing engineers put a 0. And so the Atlas variant, the Atlas V variant that carries the Boeing's EST-100 Starliner is actually called the Atlas V 022. So that's the Atlas V, no fairing, 2 solid rocket boosters, and 2 engines on the second stage. And so that's kind of also a great way to practice the naming convention. So I'm going to be heading over to the live stream of the launch now.
Coming up on 30
and I'm going to be rewinding.
The 180 is throttling down as expected. Engine response looks good. And Mach 1 Atlas V is now supersonic.
And I'm actually going to rewind it back to when the vehicle actually launched. So you can really see those 4 solid rocket boosters on the side. Okay, rocket is now on internal guidance. That's what that announcement was. The Atlas V has now passed the speed of 1. That's what that call out was. You can see the velocity readouts on the lower left here. So those RD-180s that they're talking about are the main engines that are actually Soviet engines. So that's a 2 combustion chamber variant of, I believe, the RD-190. Okay, we just had separation of the solid rocket boosters. And you can really see something that you see with all rockets, particularly well with this rocket. You'll see as the rocket goes up, the plume from the rocket engines actually expands out. And the reason for that is that there's less atmosphere to contract it into a solid plume. You can hear when they're talking about the second stage, they're mentioning the Centaur.
I can't hear it. I can't hear anything.
The frost that you can see on the vehicle is actually coming from the fact that both the cryogenic liquid oxygen and fuel of the second stage, and also the fact that as they're getting further up into space, they're depressurizing, so it's getting colder and colder. And we just had fairing jettison. I'm actually going to plug in my computer.
Mine hear you, I can't hear theirs.
Okay, so you can now see the second stage engine.
Team does a great job. As I said, they're very focused, very disciplined. As Tori also said, courageous. They have done a lot of work to get us to this point today through this pandemic, changed how they did some of their work, made adjustments as needed, a lot of cleaning, a lot of things, a lot of wearing their face masks, doing all kinds of things. And so this is an exciting time, not only for the JPL team in March 2020, but everybody that's worked this mission and for the country and the agency. So this is exciting to see. We still have a long way to go, Joshua, before spacecraft separation.
Yeah, we had a really quiet countdown today, which is phenomenal, that we got off the ground on time, and we are proceeding now that we are in the middle of the first burn. It's tough to make out, but that engine is lit and it's firing, so we are in motion. There you go. There's that animation we talked about.
The telemetry there as we switch to a TDRS-compatible data format.
TDRS.
Overall telemetry quality is very good.
The space tracking system, there you go. And we are proceeding on our video, but the first animation is tough to make out where that engine is lit, although we're not actually seeing the engine. We aren't seeing
And you can actually notice some outgassing going on the lower portion of the screen. I believe that's either from the plumbing for the rocket engine or the plumbing for the reaction control system. Okay, we're now switching over to an animation of the launch vehicle. around on the lower portion of the screen. They were actually expecting some me for the accident. The more of these going on around on the lower portion of the screen. They were actually expecting for the accident. The more of these going on around on the lower portion of the screen. They were actually expecting some me for the accident. The more of these going on around on the lower portion of the screen. They were actually expecting some me for the accident. The more of these going on around on the upper right of the screen, you'll see some of the telemetry readouts. I don't think those are live telemetry, but I believe that they are pretty close to
ultimately, a lot of people.
We've left Earth. We've got into a park orbit around Earth right now, and while we're in that park orbit, we will perform some maneuvers to kind of roll Mars Perseverance and the Centaur and coast during that time, basically setting itself thermal environments that are on Mars during this coast period. That coast period will allow us to coast into a position Mars Perseverance and fire and velocity needed to hit off and basically get this
Yeah, it has a little bit of an echo. I'm guessing that is actually coming from the live stream.
meter or two away from me on the other side of a door in a clean.
Okay, what about now? Oh, that would make sense. Okay, can everyone hear me? Cool. So looks like everyone will be stuck with my narration for the launch. I think there was some kind of weird feedback loop going with the NASA live stream that I had playing and my microphone. So here's what's going on in the current part of the launch. We've now made it into orbit with the Perseverance rover and the second stage of the Atlas V 541 launch vehicle. And the next thing that we're going to be doing is we're going to be doing a burn to get to a Mars transfer orbit. It looks like we're in a vaguely elliptical orbit. I can tell that because of these telemetry readouts up here that say that we're at a 169 kilometer by 252 kilometer orbit. What that means is the highest part of our orbit is going to be 252, around 253 kilometers, and the lowest part of our orbit is going to be 169 kilometers. How about we actually do this? If you have any questions as the audience, put them in chat, and I'll answer them. Looks like so you can actually vaguely tell that we are passing over, I believe that is either Europe or Africa. And to answer the question that Andy Berger just asked, which is why do they schedule these launches so early in the morning? The reason behind that has a whole bunch of reasons. Part of it is the weather. We weren't too sure how the weather was going to be for this launch. Part of it is the actual launch window. I believe that for this particular launch, the weather had a larger play than the launch window because they were originally planning to launch a little bit later in the day, closer to around 11 o'clock. However, I can never really say for sure as I'm not a NASA weatherman. The other reason why rockets will sometimes launch so early or even at around midnight is because of the launch windows that they need to hit. So they need to launch at a very specific time so that they're put into just the right orbit to either go to Mars or the International Space Station or whatever they want. So they're currently explaining one of the experiments on board, which is called MOXIE, which is the Mars Oxygen In Situ Utilization. NASA loves their acronyms, and this is going to be the first time that we're attempting something like this, where we're going to be taking atmosphere from Mars and trying to convert it into oxygen. And so Kirsten just asked, why have there been a couple of countries launching to Mars all at the same time? And that's actually a great question because this goes back to launch windows. And so the reason why you'll see in the past couple weeks we've had actually 2 other launches from 2 countries that are going to send something to Mars. And the reason behind that is that in order to meet the launch window, as soon as a launch window comes around for Mars, which is around every 2 years, everyone sends their stuff to Mars so that they don't miss that launch window and have to wait another 2 years before they can launch something again. So an interesting fact that you might kind of see in the live stream is every so often you'll see 2 small thrusters fire on the bottom of the second stage. And what that's doing is that's actually keeping the fuel and oxidizer stable in the rocket engine. So what they're trying to do is, in zero gravity, liquids do weird things, and they don't often behave as you want them to. Oftentimes, you want them to be at least in a known state and usually at the bottom of the tanks relative to the probe. But for this particular rocket, in order to get them to be stable, you need to provide a little bit of force because it's in zero gravity, and the liquid fuel and oxidizer is just going to be kind of floating around wherever it wants otherwise. So that's what you'll see every so often. They'll just fire a little bit of a small thruster, and that'll keep the fuel stable for when they eventually do fire up the rocket engine. Here's another interesting thing that you see on both the Perseverance and the Curiosity rover, although the Perseverance has a very slightly different method of doing it. So you'll see this kind of circular antenna, and then you'll see another hexagonal antenna on board the Curiosity and Perseverance rovers, and those are their main way to communicate with either a spacecraft that's orbiting Mars or directly with Earth if need be. Because in order to talk to the rover, it's not really as simple as dialing the right phone number and saying, yeah, I'd like you to take a picture of this particular rock. First, you actually need to get the communications out there, which can take a lot of effort. Oftentimes, you have to talk to either the Deep Space Network, which is a series of dishes here on Earth, or relay the communications up to satellite in Earth orbit. From there, you have to relay the communication over to either the Mars relay network that we have, which is comprised of all of the orbiters that we've sent there, or if you have a really powerful signal and really need to, you can sometimes get away with sending stuff directly to the rover, although that's usually reserved for emergencies. And then from the Mars relay network, that needs to relay the information down to the Martian surface where Curiosity, or in this case, Perseverance, is going to be. So it takes a lot to get a communication, any communication, just to the surface of Mars, which is one of the reasons why it can take a couple of days just to get a single picture from the camera, because you can imagine from the rover's perspective, the rover has to take the picture, then send it up to the Martian relay network. The Martian relay network then has to send it over to Earth, and usually that gets received by either the Deep Space Network or a relay satellite in Earth orbit. And so the ways that the rover communicates is that hexagonal antenna is something called the high gain antenna. That's a steerable but directional antenna. And then that kind of cylinder tube-shaped antenna is the low gain antenna, which isn't steerable, However, it requires much less power. It's something called an omnidirectional antenna, which means that it kind of sends a pulse out in a sphere, and anything within that sphere can receive that pulse. The low-gain antenna, you can see it right above one of the commentators' heads, is often used for emergency communications, like when they need to tell the rover, hey, there looks to be an object in your way, try avoid colliding into it. And then the high-gain antenna is the most often used means of communication, the preferred means of communications, where they'll steer the antenna at either a relay satellite or directly at the deep space network. And we're talking about around 20 to 50 megabit communications here, so a lot slower than even your home internet. Looks like we might be coming up on the Mars transfer orbit injection burn. Or maybe not. So here's another interesting thing about both the Perseverance and Curiosity rovers. You might notice that they don't have solar panels on top of the rovers. And the reason for that is that these rovers are actually nuclear powered. Because one of the things that you have issues with that's actually special to Mars is dust storms. And the dust storms don't really harm the rover. It isn't like a Martian situation, if you've ever watched the movie The Martian. The atmosphere is too thin for it to really harm the rover directly. But what it can do is deposit a layer of dust and sand on the rover's solar panels if it had any. And so over time, that rover will actually have a shortened lifespan because as more and more dust and sand get on the solar panels and there's no one to go and clean it off, well, they'll kill the rover eventually. However, an interesting thing about the rovers that we have sent that do have solar panels, like Spirit and Opportunity, is that those rovers lasted a lot longer than we were expecting them to. They originally had 90-day mission plans, but Opportunity was going for a couple years. And the reason behind that is that every so often, the conditions would be just right to gather up enough wind to blow the sand off the solar panels, but not enough to create another dust storm. And so what they're currently describing is actually going to be the landing site of Perseverance, because one of the main reasons why we're sending another rover to Mars is because we want to hit a very specific landing site this time. And this landing site is actually very interesting. It is a particular crater called Jezero crater on the surface of Mars. And based upon the orbital photography and previous spectroscopy samples that we've taken of that particular area, we think that that could be something of an ancient river delta on Mars, because Mars used to have a much thicker atmosphere and probably liquid water. And so based upon how that particular area looks, it looks almost as if a river delta flowed into the crater and then dried up. And we can tell that because we have situations like that here on Earth where we can see river deltas that have dried up and exactly what the sand pattern looks like. So they're currently describing the rover itself, and you'll notice this is not a small rover. These are two adult people, and next to it, it's taller than them. This rover is actually about the size and weight of a medium-sized car. And I find that amazing that we are able to shoot something the size of a car, not only into space on controlled explosions, but that we're able to hit something that is a couple million kilometers away. And not only are we able to hit it, but once we get there, we're able to do science experiments with it. We're able to make use of it. They're actually currently even describing how the sample collection is going to work. you see there's a robotic arm on the front of the vehicle, and what that will do is that will kind of come out, and on the arm it has a hand, or what they call a turret, and it'll take a sample via the drill. You can actually see that on the kind of top right here. It'll take a sample via the rock drill on board, and that rock drill will drill into the rock and kind of scoop up the sand that is created by drilling, and then it'll take that underneath the rover where they have another robotic arm that will actually cache that sample. So it'll take that sand and rock and put it in a little sample tube after analyzing it. They're currently also talking about Ingenuity, which is the Martian helicopter that we're going to send. And this helicopter is interesting because not only is it going to be the first time that we're going to be having a powered flight on the surface of Mars, but this helicopter is also solar powered. It has two coaxial, which means inversely rotating blades to keep it stable. And it isn't like we haven't tested this helicopter before, because we're not just sending this off to Mars and hoping that flies. We've actually put that exact helicopter in a vacuum chamber here on Earth, dropped the pressure down to what would be similar conditions on Mars, and tried to fly that helicopter, and based on that, we've designed it to work for the Martian atmosphere. It's incredibly light at only like a couple 100 grams, which is very light for a flying object, especially on Mars, and it's also solar powered. You can now see some footage of some background footage of them transporting it, and particularly the Perseverance film. And so where's some other... This particular rover doesn't have any solar panels, and so how it works is via something called an RTG, or a radioisotope thermoelectric generator. Yep, and we just got a comment from Harry Spears that said, yep, Opportunity lasted 14 years longer than planned, and the planned mission time was around 90 days. And so it's really amazing to see that happen. The only reason why Opportunity actually kind of died in its final moments, which was in, I believe, 2019 or late 2018, is that there was a particularly bad dust storm. Every couple of years, Mars will get these really bad dust storms that will cover the entire planet. And for this particular dust storm, Opportunity finally got its panels fully covered, so the solar panels couldn't produce enough power for the rover to really do anything or even keep the electronics warm, so it couldn't wake back up in a sense. You'll notice that the launch footage that they're currently showing is of things like the Orion capsule, the SpaceX Falcon 9 and Crew Dragon capsules, and the landing simulations of Curiosity and the reactions of mission control. Do we have any other questions? I love answering everyone's questions. So some rover anatomy for you. The head that has the cameras on it, that's up on a pole from the rover, that's called the mast of the rover, and that is actually a ship term for navigating around the rover in terms of telling the different parts of the rover. And what the mast and cameras do is they are kind of the primary eyes and ears of the rover, And I say eyes and ears because Perseverance will do something that no other Martian lander or rover has ever done, which is that it not only does it have eyes to see, but it also has a couple of microphones on board to record what the Martian atmosphere sounds like, not only for the entry, descent, and landing, but also just what Martian winds sound like. Because we've gotten a vague idea from the Phoenix lander, which had a couple of seismometers, which could be kind of tuned to listen to the wind, but we've never sent a dedicated microphone to listen to what Mars kind of has to say, in a sense. You can see the upper stage of the Atlas V, the Centaur, is currently still just coasting to where it's going to be making the Mars transfer burns. Another thing that you might notice about the footage that's currently being displayed on screen is you might say, well, Christopher, this upper portion up here where the Martian rover is supposed to be, that doesn't exactly look like the rover that they're showing behind them. And the reason for that is that that is actually a couple of vehicles all packed into one. So in order to get to Mars, that's a very long journey on its own. So along with the rover, we send a transfer stage which has some solar panels, some basic maneuvering capabilities, so it can rotate itself, and a bunch of other stuff, which basically keeps the spacecraft alive for the many-month journey that it takes to get from Earth all the way to Mars. And once you get to Mars, the journey isn't over yet because you have to get from Martian space, or actually interplanetary space, down to the surface. And you can imagine that we wouldn't want to harm any of our precious scientific equipment. So the rover is actually packed inside an aeroshell with a heat shield on the front. So that's kind of the line that you see right here. That's the heat shield. And then this white portion right here is the aeroshell. And that helps protect the rover from, when it's coming in at a couple kilometers per second, is going to be its arrival speed at Mars, to the point where hopefully the goal is to get 0 meters per second at 0 altitude with 0 acceleration, which is a very difficult goal to achieve. Only about half of all Mars missions that Earth has sent to Mars have ever actually succeeded, which is a very low success rate. But we're building off of the experience that we've gained from all of the Martian landers and rovers that we've sent there. And one of those main things is we need to pack everything up tight into an aeroshell, and some rovers, including this one, will even use a rocket-powered sky crane to lower the rover the last 30 meters or so, which I just find so cool. I mean, they're using a rocket-powered hovering quadcopter, basically, and then they're lowering the rover on a tether from that until it eventually meets the surface, and then they cut the tether, and the sky crane flies off to go crash somewhere that's not near the rover. Do we have any other questions? Okay, we're going to have main engine start in approximately 5 minutes. So we have 5 minutes of either me giving more facts, or if anyone has any questions, I'm happy to answer them. So how this particular mission will work in terms of where the second stage will go after it has fired is the second stage will actually enter an orbit around the sun. And of course, we won't be able to really control it anymore, because once it detaches from the Perseverance rover, it itself can't really keep it alive. It doesn't have any solar panels or anything to power it. However, every science mission that we've sent to Mars, the transfer stage has always ended up in a solar orbit, which is a really interesting thing because that means that here's this thing that, oh, did I mention that the Centaur stage is about the size of a bus, like a whole bus, like a school bus? And so every time we've sent, like, the Curiosity rover, in this case the Perseverance rover, to Mars, we've also sent something the size of a bus into orbit around the sun, which I just find to be kind of a mind-boggling thing. I mean, how do you even quantify what that means? I'm trying to imagine sending something about the size and weight of a school bus until it gets to a couple of kilometers per second. I mean, any normal school bus would probably disintegrate at that point, but it still seems like a really cool thing. So we're currently at T-minus 3 minutes to the transfer burn. You can see again, here's the hexagonal high gain antenna, and that's actually on a steerable mount, so it can steer around and point at the different Martian relay satellites. I believe that's the Pacific Ocean we're passing over. That's either the Pacific, Atlantic, or Indian. Since we're at 29-degree inclination, I'm guessing that's actually the Indian Ocean that we're passing over. Some other stuff. It's amazing to think that, so we made it to orbit in only a couple minutes with this particular launch. Yet it's going to take another around 45 minutes until we make our ejection burn, and another couple of months before we arrive at Mars. So that kind of puts everything into perspective in terms of distance. It's extraordinarily difficult and relatively time-consuming to get to space, but it only takes a couple minutes to get into orbit. And from there, it takes a little bit more than 3/4 of an hour to get from Earth to an interplanetary trajectory. And then from an interplanetary trajectory to actually arrive at any kind of celestial object, even if you're taking the shortest amount of time and distance, that's still going to be a couple months before you actually arrive there. So you'll notice as we're about to start burning the second stage for our transfer burn, the second stage is actually starting to become horizontal relative to the Earth. And that's by design of the mission. The way that they do it is they point it where they're going to burn, so that by the time they're at the place that they're going to burn, they're burning horizontal relative to the Earth and in the direction that they need to go. Because if they just burn directly at Earth, they'll come back down, and that'd be quite a waste of a very expensive mission. And if they burn too late, they'll be burning kind of facing away from Earth, which is not exactly the most efficient way to leave Earth. The most efficient way is actually to add enough velocity that you kind of slingshot around and into interplanetary space. And we just started the second stage interplanetary transfer burn. You'll notice that there is a very weak plume emanating from this rocket engine, and that's not because the rocket engine itself is weak, but that's just because there's not really enough atmosphere to really show the plume of the rocket engine. And this is a simulated burn, so they'll put a nice pretty flame up. But what you'd actually notice if they had any live cameras from the second stage or upper stage, you'd notice that it almost looks like the rocket engine isn't even turning on, even though it's going at full thrust and is powering about a couple 100 or even 1,000 kilograms of thrust. So you'll notice we're adding to our apogee altitude, and if they showed it here, we'd also be adding to our velocity, which in astronomical speak we call delta V. velocity, we're adding to our change in velocity. And the landing procedure of the rover, as Harry said, is very interesting actually, because it's infamously been called the 7 minutes of terror, because once you get to Mars, then you have to land there. And so the first thing that happens is the transfer stage separates from the aeroshell right before it enters the atmosphere. And then the aeroshell enters the atmosphere at hypersonic speeds, even from Mars, which forms plasma around the vehicle, so it's going really fast, coming in really hot. And then as soon as it slows down just enough to deploy a drogue chute, which is actually, cool fact, one of the largest parachutes ever made is the drogue chute made for the Curiosity and Perseverance landing procedures. So they deploy that drogue chute, which slows them down even more, and then they will deploy the heat shield off the front of the vehicle to expose the rover and sky crane to the airstream. And then eventually, when they have everything slowed down just enough, the sky crane and rover will actually drop away from the aeroshell and the parachute. That will start falling to the Martian surface, and at a certain pre-specified distance from the Martian surface, the sky crane will actually fire 4 rocket engines that will kind of slow it down enough. And then from the sky crane, the rover will actually lower on a tether all the way down to the surface before the sky crane cuts the tether and flies off somewhere to go crash. You might be wondering, why all the complexity for landing at Mars? I mean, it seems like landing at Mars is already difficult enough. Do we just want to make it that much more difficult? And the answer to that is actually no. This is technically the simplest and most reliable way to land at Mars. 2600 Crunch just asked how long until launch. So launch happened at around 5:50 a.m. Mountain Daylight Time here. However, once this live stream is over, you can actually rewatch the live stream and replay it to see when launch actually happened. But back to the entry, descent, and landing. This is one of the reasons why only 50% of Martian missions that we've sent have actually worked, or around 50%. Is that the Martian atmosphere is kind of in the Goldilocks zone for being really difficult to land on. With bodies that don't have an atmosphere, we can just use retropropulsion, where we use rockets to slow us down. A perfect example of that is how we landed on the moon. For bodies that do have an atmosphere like Earth, that makes things even easier. We can just use the aerodynamic forces to slow our vehicle down until we deploy a parachute. But for Mars, it becomes wicked difficult because it has an atmosphere, which is enough to heat things up if you were just to try and send a spacecraft or vehicle there. But it doesn't have enough of an atmosphere to really slow it down. And so what you have to do is you have to use kind of a combination of both rockets, parachutes, and protective equipment to land on Mars. It's a little bit easier than landing on Venus, because that for a bunch of different reasons, but it's still extraordinarily difficult. Again, answering 2600 Crunch's question, the launch occurred at 5:50 a.m. Mountain Daylight Time, and you can actually rewatch this live stream once it's over. Okay, it looks like we are about halfway through the Martian transfer burn. an interesting thing that happens with launches like this is that not one company is building the probe, rocket, and mission. And so one of the kind of difficulties that not many people think about when launching a mission like this is who exactly is controlling the mission? Because NASA technically is running the rover. The rover was built by a bunch of different companies. The rocket itself was built by another company, United Launch Alliance, and it's launching, and part of NASA's procedure is to have JPL controlling the vehicle on its transfer. And so it kind of is difficult to figure out, okay, whose control is the vehicle under? And that's a pretty crucial question, because it's kind of like asking, okay, once your plane takes off, if you're flying a plane, whose laws do you follow? What rules do you follow? And so kind of the procedure that is in place for ULA and NASA launches is that ULA controls the rocket from their control room. That's what we're seeing right now. But as soon as this stage stops firing and they deploy the payload, then NASA's kind of on their own in terms of then ULA hands over control to NASA to say, hey, we've put your probe in the trajectory that you wanted it. It's going to hit Mars sometime around this time. Have fun. Okay, we just had second stage cutoff, and I believe that we are pretty close to on our way to Mars. I'm probably going to have a short question and answer session at T plus 55 minutes or so. Okay, so you can see that they're currently orienting the spacecraft and they're about to deploy it. So in a couple minutes, I'll have a question and answer session. One last thing that I want to show, though, is you'll notice these kind of panels on the transfer stage for the Perseverance rover. And these panels are actually not solar panels, as some people might mistake them for. The solar panels are located on the back of the transfer stage. Those panels on the side are actually radiator panels, because an interesting quirk of being in space is that since there's no atmosphere to really regulate the temperature, you can have something that's freezing in the shadow side or the dark side that's facing away from the sun, and boiling that's in the side that's facing the sun. And so it's really difficult to regulate temperature, and that's one of the most difficult challenges, aside from the obvious fact that there's no air. And so it's kind of interesting how much thought goes into the thermal design of these probes, including things like everything from painting it white to help it not collect too much radiative heat, to including a bunch of radiator panels to help disperse the heat that is going to be generated. So I'm actually going to open it up for questions then. Does anyone have any questions about this particular mission or any other rocket? If no one has any questions, I'm just going to keep talking about cool facts about this particular mission. You'll actually notice what seems like kind of a glitch there in the simulation, where it looked like the rocket was suddenly moving down towards Earth. And the reason for that is that this is a representation of where the rocket is in space. And as they kind of narrow that down, because they're refining their simulations And eventually, in T-minus 27 minutes and 38 seconds, they're going to get the stage separation and signal acquisition. But as they're kind of refining their simulation and making better and better guesses of where the rocket is in space relative to Earth, you'll notice that show up in how the probe is positioned, and so it kind of might look like it's all of a sudden moving around. And I find that kind of weird because you would think that they put all this money into this and they can just easily track this, but that kind of puts it into perspective of just how difficult it is to both launch and even track something once it's in space. Even trying to figure out where something is in space is a very difficult task, even in modern day space travel. So you'll see we're actually passing over Australia and Micronesia and the South Asia currently. That's what you can see with these islands. Up north, I believe that's southern Japan, and kind of northwest, I believe, is China. Okay, we just had transfer stage separation, so you'll see the spacecraft just separated from the upper stage. And we're still tracking the upper stage. And you can see United Launch Alliance's mission control is currently celebrating. So for better or for worse, we're now headed to Mars. Okay, we're almost at T-minus 25 minutes until we're supposed to acquire a signal. You can see some of the ULA guys are actually probably headed home or back to work. So a lot of these guys, this won't be the only launch or even thing that they're working on with a rocket today. The launch is just, they have a launch and then they have a meeting exactly afterwards, which I find kind of interesting because you just launch something to Mars and yet, oh, I better hurry off to my meeting. I find that kind of cool, as that's just business as normal for them. So some more facts about this particular launch vehicle, because I find it interesting, and I bet that a lot of people would find it interesting, just some of the things that aren't normally thought about when discussing, like, especially the launch vehicle. Most people will focus on the space mission itself, and sure, the rocket looks cool when it's lifting off the pad and it's controlled explosions, but the build sequence leading up to the launch is what I find really interesting, because 90% of the effort really goes into that, and then the result of the effort is what we get to see. So United Launch Alliance is one of the United States launch providers, and how that works is that they get paid to build rockets. That's their job. And oftentimes, it's either for commercial clients or entities like NASA, or even other countries will sometimes say, hey, can I get a ride on an Atlas V up to this particular orbit? And what happens as soon as they get an order in is they start building the rocket itself, and that will sometimes take a couple months to a couple years, depending on what the mission requirements are. It usually is around a couple months, But once they have it built, they will start a rigorous testing process to kind of test fire the engines, make sure that everything is going well. And in the case of especially United Launch Alliance, they've gotten it down to such a science. They've tested so many of their rockets so well that they can pretty much predict exactly what will happen when they test fire the rockets and eventually fire the rockets for real. Once the test firing process is over and done with, then they actually disassemble the rocket partially so that they can transport it over to the vehicle assembly building in Cape Canaveral, where they reassemble the rocket in the vehicle assembly building and eventually put on the probe. And then they roll the rocket out from the vehicle assembly building out to the launch pad. And after they roll it out to the launch pad, then the last thing to do is some final tests and launch it, which is what we got to see today. And here's an interesting thing. I believe, if I'm not mistaken, that building behind the guy's head is actually SpaceX's hangar. So that's where SpaceX reassembles their rockets before they launch. So do we have any other questions about this particular mission? We are almost at T-minus 20 minutes until we're supposed to acquire back a signal from the transfer stage and spacecraft. So we have about 20 minutes worth of questions or even more facts about this particular mission and the rocket, and even the missions that have followed before this, because I'm happy to go into the missions that have gone to Mars before this mission. And all of the missions that have gone to Mars have followed kind of a similar form factor, at least the ones that the U.S. has sent. They've usually had an aeroshell around them and then a landing stage. By the way, if anyone has any questions, just feel free to put them in the chat. But where they kind of differed is in that landing stage, because we've tried a lot of different ways to get to Mars. Some of the most interesting ones were actually the very early methods of getting to Mars. One of the early, very successful missions that we sent, the Pathfinder rover, actually had an airbag system. And so what would happen is it would look pretty similar to the Curiosity and Perseverance rovers on its way to Mars. I mean, it'd have slightly different transfer stages and everything. But instead of having a sky crane, once the parachute deployed and they deployed the heat shield and exposed the probe to the airstream, then it would inflate a lot of airbags around the probe itself, and Pathfinder probe looked a lot like a tetrahedron with it looked actually kind of like a lot of grapes, because they had these airbags formed in a tetrahedron shape, and they would drop it and it would bounce. And that was how it would slow down, is it would bounce across the Martian surface until it eventually stopped bouncing, and then they would deflate the airbags and open up the probe, which is kind of one of the weirder ways that I've seen that we've had a successful way of getting to Mars. I mean, try to imagine, like, sending this extraordinarily fragile equipment, oftentimes made of glass or silicon, and having it bounce across the surface. And these were not small bounces, and this was not a light spacecraft. This spacecraft weighed a couple of tons, and these bounces ranged around a dozen meters above the Martian surface. And so that is just something that's one of the missions that was sent. One of the other missions that was actually sent by Great Britain is the Beagle Missions. And these are kind of notable because we're not really sure if they worked. We know that Beagle 1 crashed into the surface of Mars and didn't work, but Beagle 2 might have actually soft landed at Mars, but landed upside down, which is kind of a weird way to fail. Because the Beagle 2 mission, how we can tell that it might have landed upside down, but we're not really sure, is that it kind of unfolds like a flower. That's how the Beagle mission, the Beagle landers deployed. And we could actually see somewhat of that from space, from the orbiters that we have around Mars. But we couldn't make out enough detail to tell what side was right side up on the Beagle 2 lander. And so for all we know, that lander could have landed perfectly fine, but have just been upside down or not had its antenna pointed. Something that they're showing currently is one of the ways that we're planning on sending humans to Mars. And something that I want to draw attention to is the power plants that they just showed, or those things that looked kind of like flowers on the surface. And those are interesting because, of course, we're going to try and send a nuclear power plant to Mars because solar panels will get covered in dust in a pretty short time. However, if we're going to send a power plant that's going to both provide enough power for humans to live, to run the life support equipment, and also be safe enough to operate around humans, especially humans that can't exactly come back anytime they want, we're going to have to make some changes to that. And that's one of the areas that NASA is making a ton of progress in, is in the development of nuclear power plant technologies. And so it's one thing that people kind of get scared about is nuclear energy. They think meltdowns. And there are a bunch of differences that make nuclear power plants built for space missions very different from nuclear power plants built for here on Earth. One of the main differences is actually how the power plant operates. So here on Earth, they operate based off of a fission system where the nuclear fuel rods heat up water in the tank, and then that water turns into steam, which powers a steam generator. But on Mars, you can imagine it's going to be a little bit too cold and probably a little bit too dangerous to have any kind of water or steam, even if in a container. And so how they operate deep space missions and any mission powered by a nuclear power plant that NASA does anyways, and a bunch of other countries, is they have something called an RTG, or a radioisotope thermoelectric generator. And that's a really fancy term for saying something that heats up and generates electricity. And so they have a lump of plutonium in the core of the reactor, and then that lump of plutonium, since it's radioactive, naturally gets very hot, and they're able, instead of using water, they use a bunch of thermoelectric generators, which are devices that use chemistry to turn heat into electricity, which involves a ton of fields of science. And they use those thermoelectric generators to generate the electricity directly from the radioisotope. And those have a couple of benefits. For one, they're much safer than general nuclear reactors that you might find here on Earth. I mean, you could probably puncture one of those, and it would be okay, because the whole idea is that the radiator fins on the outside and the thermoelectric generators work together to keep the whole reactor cool. And relatively, they're very simple and lightweight. I mean, the nuclear facilities that we have here on Earth, they can be absolutely enormous. They can sometimes be about the size of a small town or city. But we can't exactly send something the size of a small town or city into space quite yet, or all the way to Mars quite yet. And so we have to make everything that we send as light, simple, and reliable as possible. And these particular radioisotope thermoelectric generators have an interesting quirk to them. Because they have to use a very high-grade plutonium, because it has to be naturally warm to the touch, in a sense, they actually use weapons-grade plutonium, which number one, I find really cool that they're using this thing that was originally used for fear and destruction. They're using it for good, and they're using it for something that they can actually do good with and do science with. But also, they have a limited supply to this. They have limited access to this supply because we're no longer making weapons-grade plutonium, which is a good thing. We've moved on since the times of the Cold War when that was kind of necessary to make that. And since we're not making it anymore, it's kind of become a non-renewable resource. Any plutonium that we use is plutonium that we no longer have. And so they really have to balance, okay, what missions are really going to need a nuclear reactor? What missions can we not do with solar panels? And this actually makes itself apparent in that we've been trying to reach further and further into space with solar panels. I mean, the Juno probe that launched recently, that went out to Jupiter. And normally anything that goes out to Jupiter or beyond requires solar panels because out beyond Jupiter it requires an RTG because solar panels just can't provide enough power out that far. And you can see this in the Juno probe's design. It has 3 enormous solar panels that are much larger than the spacecraft itself and probably are much heavier than the spacecraft. But it requires that much solar collecting area just to power a small probe. So we're about almost 10 minutes from signal acquisition. Some of the other things with radioisotope thermoelectric generators, though, is you might be wondering, why, if they're so good, why don't we use them here on Earth? And one of the main reasons why is that comparatively, they're relatively inefficient compared to the processes that we have here on Earth, and they don't produce much power. I mean, the RTG on the Perseverance rover will produce a max of a couple thousand watts or a couple kilowatts of power at max output. And that's just not really enough to be feasible for a large power station here on Earth. I mean, that's barely enough to power a couple homes. But it happens to work just perfectly for a small or even large space mission such as this one. Some other notable things about the Perseverance rover is that it is one of the first rovers that we're going to send that is going to have a bunch of memorabilia, in a sense, on board. It'll have a bunch of plaques and stuff that don't necessarily contribute directly to the scientific goals of the mission and of the rover, but that are going to be pretty more useful than you might think. This is going to be an example of stuff like the Voyager probes that we sent out. We knew that they were going to go interstellar, and we know that they were going to survive for a really long time. So we decided to include plaques and discs and stuff that if anyone happened to find it after a couple hundred years, they could roughly figure out what humanity was. And we have kind of the same thing going on with this rover. We have a laser disc or glass disc that has data from thousands and thousands of names. I think that Harry even has his name on the Perseverance rover. And we have a bunch of different plaques for everything from the name of the rover, Perseverance, which is prominently displayed on the front arm of the rover, to even stuff like telling any Martians that might, or any extraterrestrial life that might find the rover, where Earth is in the solar system and what we were when we sent this. And I find that kind of interesting because NASA and no one really knows if there's extraterrestrial life. But one thing that we can do is, even if we don't know, we can prepare for, well, if there is extraterrestrial life, but they happen to get here a couple hundred or thousand years from now, humanity might not look the same as it does today. So let's send out like interstellar and interplanetary time capsules to show what humanity was. Okay, and it looks like we may have just lost the live stream, perhaps. Okay, so we've lost the NASA time stream. So I'm going to ask one final time if we have any other questions, and then that's going to be the end of today's launch coverage. We have launch coverage back. And looks to be fairly unstable, but we'll see where it goes. We'll hang in there until we get either signal acquisition or we lose launch coverage again. And here's an interesting thing about NASA as a whole that not a lot of people know. So NASA, by law, is required to release a lot of their stuff to the public. So the images that Curiosity has taken and the images that Perseverance will take will be available to the public. These are not things that just scientists have access to. And if you wanted to access these images, you can easily go to NASA's website and actually find the pictures that Curiosity has taken, and even some of the science that Curiosity has done, which I find really cool because it really shows that NASA's not in this for any other reason other than to spread knowledge about this. There's no ulterior motive here or anything else. It's sheerly for the goal of sharing knowledge with humanity. And that's a fairly rare thing in this day and age. And so I think that that's a thing that is incredibly important to keep in mind with space travel. So as we approach right about when we're going to have signal acquisition, I'm actually going to talk about some of the other missions that have been launched during the Mars 2020 launch window, as it's called. And there are two other notable Mars missions. There is the Tianwen-1 Mars mission launched by China, which is a kind of 3-in-1 probe. It's going to have an orbiter, a lander, and a rover all on board. And that was launched a couple days ago, or maybe even around a week ago. And the other notable one was the Hope Mars mission, which was actually launched by the United Arab Emirates, which was a very interesting mission because it was launched by a Japanese launch vehicle. The mission is going to be run by the United Arab Emirates, and some of the instruments were built in the U.S. So it's kind of an international collaboration, which again shows that space is not something that belongs to any one nation. And it's something that no matter what is going on down here on Earth, space is something that we as a species can collaborate on getting to. And so some of the other interesting parts about these two Mars missions especially is that like the Hope Mars mission is going to carry something called, I'm forgetting the exact acronym for it, but that it's going to carry a spectrometer that was built by my university, Arizona State University, and I actually got to see that instrument I was actually only a couple feet away from that instrument when it was being built. And it's a really cool thing to see because here you have this instrument that's about to head to Mars, but it was built by people. It wasn't built by anything like, it wasn't, we can often forget that these people are people, and that in order to get to space, it requires the efforts of not just a few people, but a ton of people, and from all different professions. I mean, NASA even releases pretty often two really very interesting booklets. One is technologies that have come from space to help Earth, in the sense of technologies that NASA has built for spacecraft that other people have realized, hey, that would probably work really well for this. A great example of that is the guidance computer for the Apollo missions. That was the first computer that didn't require a whole room and a ton of air conditioning to work. Before that, computers needed huge rooms and entire facilities to operate. But because of the developments made by the space requirements for that computer, they were able to bring those requirements back to Earth, and those are kind of have become personal computers or PCs. Just a little bit ago, we actually saw something that showed three cones emanating out from the Earth, and that's actually something called the Deep Space Network. It's a series of dishes around the Earth, of ground-based satellite dishes around the Earth. There's one in the Woomera Launch Complex in Australia, there's one in the US, and then I believe there's one either in Europe or somewhere near there. And what those do is those are kind of our walkie-talkie to Earth. And so any space mission that we send out, it has to somehow be able to communicate back to us. And the Deep Space Communications Network is how we receive the signals from those spacecraft. And those are actually long-range networks, so they don't operate too well when you're really close to them, like in low Earth orbit, which is only a couple hundred kilometers away. But they operate really well when you are a couple million kilometers away. Okay, it looks like we are almost T-minus 1 minute until we're supposed to acquire signal. You can see they have a live stream from the mission control at JPL, where they're currently starting their work to figure out exactly what might be going on, how they're going to acquire the signal, what's going to go on in terms of, they have a bunch of procedures for that. You can actually see this area down here is the telecom, so the communications. And they're currently going to be talking to the flight directors, updating them on anything, on any updates that come across for them. Looks like we have an update coming across, and one interesting thing that you'll notice about how they communicate in JPL and really any mission control is they try and keep talking to a minimum. And it looks like we have signal. Okay, so you can see everyone just clapped a little bit, and then they got right back to work, because now the real work begins, and now these people are going to be monitoring everything, bringing every system up, and in a couple of months, we will arrive at Mars. So does anyone have any final questions before we close up the live stream? So if anyone has any questions after this, feel free to re-watch the live stream. It'll be posted up on YouTube, and comment on the video or message me directly, and I can answer any questions that you might have. With that, I'm going to sign